Oh, Luke,
Hi.
you're the first to join.
Yeah, I guess so.
Rotate it. Oops, where am I? I think I'll leave it to the classroom. How are things?
Pretty good.
So I attended your talk
Uh-huh.
and in the quantum seminar. That was nice. I was just wanting to know what and how you were involved in. So have you presented this before anywhere else?
No, this was the first time.
Oh, this was the first time. Did you enjoy giving the talk?
Sort of. I was struggling to come up with a good structure for the talk. So a lot of the practice that I did, I had to tweak it. So I never really got a full run through of that version of it. So I felt like I wish I had been able to get the structure down earlier so I could run through the same presentation to feel a little more confident. But I was at least pleased that the structure was good. And I think when I gave it on Friday, the pacing was also good, which I was pretty worried about because my practices had been way too long or yeah, so
yeah, I think it went well. You seem to have a good idea of
Gotcha.
I was just interested. The topic attracted me. Yeah. Actually, talking about this, you do realize that in math there are this graph. Are you aware of graph theory?
Yes. Yeah.
So there might be people interested in the math department. And there is a spot, you have attended a few potpourri seminars, right? Do you think you'll be able to present something of this, a smaller version of it, not the whole thing? I'm not sure whether you might be able to convey the whole thing, but just even though it is a popular problem, traveling salesman problem, that's the idea that you're able to give a quantum version of it, or at least motivation along that direction. Anyway, think about it. I don't want to say anything more on that. Yeah.
Okay. Yeah, I'll think about it.
Yeah. Again, if you enjoyed the group there, it's a small group and they're just curious about things. So only if you feel comfortable. Yeah. Don't go out of your way to do it.
Yeah.
Or anything you in general find interesting.
True. Yeah, thank you for attending.
Oh, no, I was just curious. Yeah. That was the first time I attended during the online.
I see.
So it was different. I've attended it actually 1 or 2 semesters I used to attend it regularly, but then I gave up because I was not really understanding the uh, whole general scenario, what the purpose is, or I was not aware of the notations probably.
Right.
It was a little technical.
Yeah, I'm still getting used to the notation. So a lot of times I don't follow very well, but
Yeah, that's part of getting into a field that you need to know what others are doing, kind of the notation is. That's one hurdle. Let's see. There's no one else coming here. What's happening?
yeah, I don't know.
We'll give it a few minutes. I don't want to make this a habit, but I think I noticed that this class, probably because it is too early in the morning, I think everyone is often late. But since it's a small group, I think I'll wait.
There we go.
Oh, here you go. Alia.
Hi, Alia.
Hi, Luke. Hi, Professor.
Hey. I was thinking you will also, no one joins and then I don't have to teach.
Oh no, uh, I I haven't tried, but I think there is internet problem.
No. Oh, yeah. Yeah, let's begin so that I think others can use the internet anyway, or use the, what do you call, the recording anyway. Any general comments? Oh yeah, we have Michael also now.
Hi guys.
Okay, so I think almost 10 minutes down. So you can use the recording. Okay. Any general comments on how the course is going? You guys want to say anything? No. Okay.
Not really. No, I
Yeah,
think it's
sure.
I think it's good.
Okay. So we have a few things going on. So we have homework 9. Due November 19, that's 1 week from today. And we have finished all the midterms. Did I grade your midterm? Oh no, you haven't submitted yet, I suppose, or at least last checked. Yeah, okay. I said that it is possible, it is okay to submit later also. Okay, so it's the final exam. Which will also be take home. It's officially on Tuesday, December 8th, between 8 to 10 a.m. Which means that this is your deadline. Like everything has to reach me by 10 a.m. Not only that, like final exam has to reach me by 10 a.m. That's strict in a sense, and all submissions has to come by December 4th, Friday, 12. 11:59 p.m. And even those late submissions, like at least until homework 8, most of you guys have been pretty punctual, so I will keep that. I don't think I'll accept late submission for that, but after that, it is free. You can submit it anytime before this. But at the same time, I've been recommending that often it gets too much at the end, so you don't want to pile up everything for the last day. Ah, here we go, Moses. Yeah.
Sorry, I'm late.
Yeah, I think most of us. No, I was on time. Most of us were right. So we have Moses here. Yeah, we are not begun yet. So show them your face in these pandemic times. In this pandemic times, it's what is it? Would you say it's fortune or something? It's a pleasure maybe to see faces.
Yeah.
Okay, so let's do something. We started on Bessel functions. And we're going to be very short introduction here of Bessel function, primarily orthogonality, and sometimes addition theorem also comes in. Whatever is very much used in physics, that's how we're going to introduce, and with the limited time we have. So we did define, so you can say an integral and integral representation of Bessel function, and let's say of 0th order, right? Later we'll come and define of the mth order. Also, so this is J0 of t. It's equal to 0 to 2 pi alpha the Bessel function is dependent on two quantities. This is the argument. No, this is the order, right? That's what we mean by 0th order. And that's the argument of often this order is integer, but that's not necessary, right? Most of what you see now will be integer. Actually, no, when you do a spherical problem, say a problem with spherical symmetry, it becomes half integer, but still it is half integer problem. But very quickly, if you're doing more involved problems, if you're working in higher dimensions, for example, then these things will immediately get into continuous regions, and there are very powerful statements you can make on that. It's the same thing as whenever you have a variable, you can start with discrete, then you can go to real, then you can go to complex, and in principle, generalize it as much as you can, just as a mathematical exercise. So same thing here. Anytime you have a variable, you can ask what is the region of validity of this function. At this moment, we are just going to keep this as integer. Okay. So this will be integer, but doesn't have to be. This can be generalized. And argument t will be real. Again, these things can immediately be extended. Is alpha a variable here? No, notice, because it's an integral. After you integrate, you are left out with only t and m. And in principle, this will be an mth order, but since it is 0, it doesn't show up on the right-hand side. We'll later down the line generalize this to mth order. An integral representation is typically harder to visualize because the structure of this function, for example, as t increases, does the Bessel function increase or decrease? It's not very obvious because you do the integral and then visualize that in your. So due to that reason, it is a little harder. It's the same thing as a sine function. If I were to give you sine theta is equal to theta minus theta cube over 3. No, what is this? 1, yeah, right. Theta phi over phi factorial and so on. And if you did not know the functional form of sine theta, this is actually periodic, it is harder to see that on the right hand side. If you were to begin with this to see all the properties of a sine function, usually harder. Of course, everything can be done from the right hand side, but it's usually not as straightforward as you can if you have a closed form solution on the right hand side. So that's what we have. And let's see some properties of Bessel function. The first thing this comes to your mind is that is a Bessel function real or not, right? Suppose you evaluate this for a certain point, is it real or not? And one would think that it is actually complex, right? Because exponential comes in, that has to be a complex term, but it is actually real. So you have to prove it, right? So it turns out that it's actually real. So the first thing we do is, let's see what is, whether it is real or not. One thing you can do is that just show the imaginary part is 0, right? That's one way of doing it. Or we can do the star complex conjugate and show that subtraction between the real and complex conjugate is 0. But let's expand this out. Let's see the imaginary part of J0. So imaginary part of J0t. Will be equal to expand this out cosine and sine. So this is equal to 0 to 2 pi alpha over 2 pi. Remember, because exponential is cosine plus I sine. So this will be sine of t cosine alpha. And the proposition is that this is actually 0. So how do we see that? So let's break this up into 2 regions. It's an integral that is 0 on each piece, right? Whenever the integral is 0, it is the area under this functional curve that is 0. That gives us an idea that our sine function is actually 0 to 2 pi. It oscillates, maybe it cancels out. So let's break this integral into 2 regions. Right? So it is 0 to pi the alpha over 2 pi sine t cosine alpha plus pi to 2 pi that should be perfectly fine. And let's do the second integral. And our goal will be to show that it actually cancels out the first integral, right? That will be a way of doing this. Then alpha goes from pi to 2 pi. So in the second integral alone, let us substitute alpha prime is equal to pi minus alpha. So that way I shift this limits to 0 to pi. So this is d alpha prime is equal to 0 minus d alpha. And the limits, when alpha is pi, this is that what I want to do? Maybe 2 pi minus alpha. No, it's okay. So Yeah, let me do not pi minus alpha, let me do 2 pi minus alpha. Probably that would be better, but either way should work. So alpha, when alpha is equal to pi, this is equal to pi, and when alpha is equal to 2 pi, this is equal to 0. Alpha is equal to pi, this is equal to pi, and otherwise it is 0. The alpha is minus d alpha prime, so it's minus d alpha prime over 2 pi, and we have sine of t times cosine of 2 pi. So alpha is 2 pi minus alpha prime. So I keep the first integral as it is. I use a negative sign to change the order of the integral. Am I doing this okay? Oh, yep. Okay. Why am I struggling? So minus is used to flip the sign of the limits. So it is 0 to pi, the alpha prime over 2 pi times sine of cosine of 2 pi minus alpha. This cosine function is, that's your cosine function. So 2 pi is here, that's your 0. 2 pi minus alpha is pretty much cosine alpha itself. Make this to be alpha. If you subtract the same thing just by the symmetry, you can see that that will be the same. So 2 pi minus alpha is the same as cosine of t alpha. What happened? Let's do this correct. Alpha prime is equal to 2 pi minus alpha, but it doesn't seem to cancel. It's okay. All right, it should cancel. Thought it will cancel. Okay.
Why doesn't it? Why does it not cancel?
Huh?
Why does it not cancel?
Oh, because I thought these two are the same, correct? So they are not canceling, they're adding, right? Like this integral and this integral are the same, so you just add up, right? So it is 2 times that. I expected this to come with a negative sign. Isn't it? Or I'm messing up. So if 2 pi minus 0 to pi and pi to 2 pi. Pi to 2 pi, I said that, okay, I will do it from 2 pi minus alpha. Yeah, this is okay. Alpha prime is 2 pi minus alpha. So when alpha is equal to pi, that's pi. Alpha is equal to 2 pi, that's 0. The alpha prime is minus the alpha. That's this minus. We should flip this. And that stays the same. Okay. Why not?
What if it were that cosine 2 pi minus alpha is the same as cosine minus alpha?
Cosine, is it minus? If it is minus, then I'm good. Cosine of 2 pi minus alpha, I thought was sine alpha, right?
Yeah, but isn't it, could you not also say that it's minus cosine minus alpha? Like just neglect the 2 pi and just do cosine minus alpha and then take the minus.
No, cosine of minus alpha is the same as cosine, right?
Yeah, okay. Yeah.
So in the fourth quadrant, usually cosine is positive.
Yeah.
Right? how did I? Mike. Yeah. I substitute alpha minus 5. What's wrong with this? There must be a mistake. Okay, how about this? Give me a minute, okay? I think there is a mistake in this. Or is there not? Okay, keep that. Seems like there is nothing wrong there. Agreed? So let me do this again. So this is alpha, so pi to 2 pi, the alpha over 2 pi, sine of t cosine alpha. And I substitute this time, alpha prime is equal to pi minus alpha. I'm allowed to do that. Right. So this time, I have d alpha prime is equal to minus d alpha, same thing as earlier. But the limits will change now. Alpha prime, when it is alpha is equal to pi, this is equal to 0. When alpha is equal to 2 pi, is that what I substituted? No, alpha minus pi. That's what it is. Doesn't matter, like I feel like let's stick to this one so that I see how you can get it, and let's see what's wrong. Okay, so when alpha is equal to pi, that's 0, alpha equal to 2 pi, this is pi. D alpha prime, that's also okay. And that's sine of t of cosine of alpha prime. No, alpha is pi plus alpha prime. And now you see that cosine of pi plus alpha prime is minus. That's better. Sine of alpha prime, correct. And you would get that to be 0. Correct. But how can both of this be correct? Okay. That would seem to suggest, if both of this is correct, that seems to suggest that this itself is 0. Right? So this is also correct, I think, because I don't see any mistake in this. So this seems to suggest that this itself is 0. Okay, so yeah, so this is equal to 2 times 0 to pi d alpha over 2 pi sine of t cosine alpha. And since these two have to be the same, there is only one way that can be true, I think, is that, not these two, this and this has to be the same. So that seems to suggest that that is 0. So can we show this somehow? How about odd or even? Suppose I were to substitute yeah, just because of these two, correct? So my claim is, actually this is a proof, right? I don't know what I can do more than this. So the claim is that this itself is 0, even though there's nothing wrong in this. This is also correct, but this is equal to this means that this itself is 0. You don't even have to go to 0 to 2 pi. Right? That has to be true because this quantity is equal to this quantity. Right? So two same identical quantities is the same with the opposite signs, so that has to be 0. Am I right? Any thoughts or argument on it? I was a little confused that way. That I thought this has to cancel. This is a positive quantity. the negative quantity? No, this itself is 0. So, and how do I show that? By doing this, these two are equal. Right? How about this? Extra credit, right? What I suggest is, if not anything, if you can prove this, I think I proved it, like this is one proof, but whenever you have one proof and you want another proof, these days you have one easy thing to do, right? You can numerically do this. Put this on the computer and evaluate this, the left hand side, and show that that's actually equal to 0. Okay. So extra credit is new. Do you guys know how to numerically evaluate something in a very simple manner? Not using a, like, of course you can do an integral using fortran and all that, but using simple mathematical programs. So you can, so if you do n, okay, first there is a command integrate. Right? This is Mathematica. So you would do, let's say, some sine of t cosine alpha. Right? So that's the actual syntax. Right? And then you will go from alpha 0 to pi. And often this may not be able to do that integral. Sometimes integrals are not doable. It may not be able to do it. So you will say that, okay, I don't want the full integral, but give me the numerical integral. So then you just have to put an n in. So that's very convenient. Sometimes you just, so you can give you a number for this. But here there is a factor of t there. So you want to put in the number here, right? Because whenever you're evaluating a number, computer cannot understand a variable. So put a 3.0 there. Or some prime number which doesn't cancel out easily. And change these numbers and see that it always gives you 0. So that's one simple test you can make. But I think this is a proof that this is actually 0. Okay, so I got distracted. Okay, so anyway, as far as our goal goes, the imaginary part of this is equal to 0. So that means that imaginary is gone. This is also equal to 0 to 2 pi alpha over 2 pi times cosine of t cosine alpha. That's also true, is it? This immediately allows us to see that if I were to substitute J0 of minus t, how is it related to J0 of t itself? When I put a J0 of minus t, I put a minus t there. Cosine of a negative argument is the same as the cosine of a positive argument. So this is J0 of t itself. So it's an even function. What is J0 of 0? J0 of 0?
Alpha over 2 pi at 2 pi minus 0.
Yeah. Yeah.
So it would be 0, 1, maybe 1.
It's 1, correct? Because when t is equal to 0, this is gone. Cosine of 0 is 1. Integral of d alpha is 2 pi. There's already a 2 pi in the denominator. So that's equal to 1. And if you were actually to plot this as a function of t, so it starts from 1. So that's J0 of t. It starts from 1. And since this is cosine, but it's not very obvious why this will be oscillatory, so this would be like this. It would die off. Right. And then various questions comes in. How does it die off? what's the power law for its decay and so on, and we will think about this as we proceed. It is also interesting to find out what is the zeroth here. Like at what point does this go to zero? Right. So whenever you have a function, you have to look for its properties. Like this is a defining property of that function. What is this? What is this? So these are called the zeros of Bessel function. We won't be able to talk much about that, but we will talk about how does it decay. So those are the questions that comes in. Okay. So that's one thing. Let's Bessel functions, the way we introduced it, it came out as a solution of the Laplacian, right? We said there is a Green's function, it satisfies that. So, so remember your Green's function satisfies the Laplacian, right? So G is equal to 0. Let me say this is over 1 over r minus r prime. That's the electric potential due to a point charge, and this is the electric field, divergence of the electric field. One derivative gives you the electric field, two derivatives gives you the charge density. And charge density exists only at one point, and that is r prime. So it is equal to 0 everywhere.
Can you turn the camera?
Unless you are observing it at r prime itself. So it's like a charge density. So it is equal to 0 everywhere else.
You turn the camera.
Oh,
yeah.
Yes. Thank you. I should make this covering. So I was saying that the electric potential due to a point charge satisfies the Laplacian equation because the first derivative gives you the electric field and the second derivative gives you the charge density. Charge density is that of a point charge, which is non-existing, which is 0 everywhere other than r equal to prime. For that, we have an integral representation for this, and that is that it is d cubed k. So if I were to do that in all three dimensions, I have e raised to I k dotted with r minus r prime, and g of k, which was 1 over k squared. And that's also equal to 0 because 1 over r minus r prime can be written in terms of this. This is equal to 0. So this was one of the integral representation for the point charge. But that's not what I'm interested in. Notice this is all d cubed k, k. The Laplacian doesn't see all these things. It sees only the r. This hits this, and that means that this should be correct. So this should satisfy 0 independently. You can put an r prime, but it doesn't see r prime anyway. So this is equal to 0. This implies that this is a solution of the Laplacian. Okay. So similarly, let's do, but we have another representation, and that is that this is equal to minus del square times, we said if I were to do this for 2, remember your, what was your Green's function? So Green's function was r minus r prime. This was equal to d2 k per over 2 pi square e raised to I k per. And that was e raised to minus k per z minus z prime over 2k per. That was our solution or an integral representation, but then we identify Bessel functions in this. One of the k prime k pubs got cancelled in our last week's our last lecture, and we said this is 4 pi epsilon. No, there's no 4 pi, right? There's no epsilon naught. Where is an epsilon? I think there is an epsilon naught. So it's 1 over 4 pi. But I'm not interested in the factors. You will see what I'm doing. So 0 to infinity now, sorry, infinity dk per times J0 of k per times r, we call this p. You want only the structure here. This. Where p is equal to r minus r prime per. Right, this was our relation that we had in the last class. This seems to suggest that this term should also satisfy the Laplacian, right? If this satisfies the Laplacian, this also should satisfy the Laplacian. So in that sense, right? So you can just motivate what is the Green's function, what is the differential equation for this. So this is k per times t times e raised to minus pi k per times z minus z prime. Choose r prime, and this is again r not equal to r prime. Because otherwise this will be a delta function on the right side. So seems like if I were to choose r prime and r, so if I were to choose this to be equal to 0, let's choose. I'll prove this more. This is, at this point we're just hand waving, but once we get a feel for it, we'll actually test it. So then this will be just minus del square times J0. There's only one or per, so I'll say that's the radial vector or per is equal to rho, right? That's a cylindrical coordinate. So maybe that's what it is, and we know what our differential equation or the gradient looks like in the cylindrical coordinates. So this is equal to minus of 1 over rho d by d rho d by d rho, correct, plus 1 over rho square plus and this whole thing multiplying on J0 of k rho times exponential of minus k per z has to be equal to 0. This should be visualized as, like, as far as the radial component goes, it is a Bessel function that is important. When it comes to z coordinate, it is exponentials are the solution for the Laplacian. So that's what we are looking at this. Since we have the charge, we chose this to be at 0. This doesn't contribute. So this is equal to 0. d by dz square, it brings down a minus k per each time it acts on it. So it seems like 1 over rho d by d rho times d by d rho plus, so minus, so the plus k, so plus 0 plus k per square. of J0 is equal to 0. But once I reach this stage, there is no dependence on z, so I can drop the exponential, because exponential is not 0 ever, so I can drop this, right? I can cancel this out. Something multiplied by something is 0. If that is not equal to 0, the other one has to be 0. So that seems to suggest that the differential equation for the Bessel function is this, right? This is case third. So that's a suggestion. So is that completely correct? Because we hand waved a little here, because in the beginning it was not very obvious how we would identify this thing. But we should be able to verify this, since we have an expression for J0, we have an integral representation. Let's substitute that in here, and let's actually verify that actually this gives you 0. So then we know that, okay, well, that's your differential equation. So let's check this. So for checking that, so let's start with our actual integral representation. It's k. Let me not write k part, let me just write k rho here. So that's equal to 0 to 2 pi e alpha over 2 pi e raised to I t, but t is k times rho, the sine of alpha. That's your Bessel function. Take the first derivative, right? Take the first derivative and then multiply it by a rho of J0 k rho is equal to, I take the derivative with rho, that hits this, that's the only place where it hits, but I know how to work out an exponential, but I'll put whatever comes out inside the integral. That's I k cosine alpha times e raised to I k rho cosine alpha. Like, this is a new technique we are learning, is that without evaluating the integral, work out something, right? Work inside the integral. Right? We're not really evaluating integral, because we know that that cannot be done. So that's what this is. But then we have a rho also there, right? So rho can go inside and outside the integral. It's just this cosine alpha cannot go. So I put in that rho here. So it's I k rho. Okay, so let's keep it as it is and bring in the next integral. So I have d by d rho by d rho. Now, when I take the second derivative, it can hit two places. I can either hit this rho here, or I can hit the rho there. There are two places it can hit. So I have to evaluate both derivatives there for two terms. 0 to 2 pi alpha over 2 pi. When it hits this, it's simple. It's a constant comes out. So it's I k cosine alpha. And instead of writing that right here, I will write it here. Right? Here. When it hits the first term, I get this times this. When it hits this, I get an ik alpha downstairs. So that's plus ik, the rho stays as it is. This ik cosine alpha squared, and then there is a rho. Then the exponential stays as it is. Right, that's just a way of writing. Okay. divide outside the one more row there. So there's 1 over rho. Zero, okay, it's equal to 0 to 2 pi alpha over 2 pi. And divide by a rho. Divide by a rho. I k cosine alpha over rho. And when I multiply this out, first the rho cancels out, and this is minus k squared cosine squared alpha. Our claim is that this whole thing is equal to 0. So the minus sign doesn't matter. So I'd add a plus k squared. So let me add that plus k squared. That's plus k squared. Again, notice how we are working on an integral without actually evaluating the integral. If I put in a plus k squared, again, it is plus k squared times Bessel function. Bessel function is the outer exponential alone. It is I k cosine alpha over rho minus k squared cosine square alpha. And then I just add a plus k squared. Right? Because that's a multiplied by 1, which is exponential. It is a Bessel function. Ask me if it is clear, like certain things might be new for you. So as a J0, I expanded this as an exponential. But this is sine squared, right? 1 minus sine square alpha is sine squared. It's equal to I k cosine alpha over rho plus k squared sine square alpha. Okay. And it seems like we are proposing that this is actually equal to 0. This integral is 0. Again, like earlier, we don't want to evaluate this integral, but actually in this case, at least if it is 0, one should see it more explicitly, right? So a trick here is that use integration by parts, right? Maybe this is an actual surface integral, and at the 2 points, this gives you the 2 terms. The trick is to realize that this is actually equal to, so let's verify that. So the suggestion is that this is the total derivative of, so let's say d by d alpha of, let's see, so this is k times sine alpha times exponential of I k rho sine alpha. This is a total derivative, that means it contributes only its boundary, but let's see if this is the same or not. So let's check. If I were to hit this quantity here, correct, sine alpha, I should get a cosine alpha, but that doesn't seem to give you that, right? So I need to put in rho, right? Rho. Okay, so there's two terms. I can hit an alpha with this or here. When I hit this alpha, that sine of alpha, it becomes a cosine alpha. Right. So k cosine alpha over rho, then exponential. That's the first term. And there's an I there, so I should put an I there. So when I hit this alpha, I get the first term. The second alpha is down there. When I hit that, this is an exponential. It gives me back the exponential. That's that sitting there. But when I hit the alpha, I should get back this whole thing with the derivative of that. So that is an ik rho. One of the rho cancels this. Ik and ik. And then cosine alpha becomes a sine alpha. That's your sine square alpha. There is an I square which was -1, but the derivative of cosine has a negative sign that takes care of that. So this is actually exactly equal to the other, right? So that's a, it's not very straightforward, but one realizes that that's equal to that. Once you realize that, then it is even easy to evaluate this integral because this exists only at the surface, right? So this is 1 over 2 pi. Ik sine alpha over rho ik rho cosine alpha evaluated at alpha equal to 2 pi and alpha equal to 0. But at both points, sine alpha is 0. That's explicitly 0. I don't even have to worry about exponential. So that's indeed equal to 0. Because sine alpha is 0 at both. So it is indeed the differential equation for the Bessel function is the cylindrical differential equation. And this is when there is spherical symmetry. This is for m equal to 0. We haven't yet introduced the mth Bessel function. And it will turn out that if I were to introduce this term here, that's exactly equal to the for the mth order Bessel function. So just based on Green's function, just getting motivation from Green's function, we have motivated that that's your differential equation for the Bessel function. It is also good to notice that this operator here, 1 over rho d by d rho, so rho d rho is also equal to second derivative of rho squared plus 1 over rho d by d rho. That is, that's got by looking at the derivative at the first one. This second derivative, not the first one, second derivative can act on this or whatever is on to the right. When it acts on this, this gives me this term. But when it acts on that, the rho cancels out and gives me this. So you should be able to see and immediately observe that these two are the same. And often there are nice features that comes up. So often you will see the Bessel function differential equation written using this structure here. So let me make this here. So Bessel function differential equation, 0th order again, is 1 over rho d by d rho rho d by d rho plus k square of k0 k rho is equal to 0. Or if you want to write it in that form, it is plus k square this, of course, is written in terms of dimensional quantities. The rho has the dimension of distance and k is unnecessarily sitting there. I can always substitute k rho is equal to t. Right? In mathematical descriptions, often you work with dimensionless variables. And then everywhere there is a rho, you just have to replace it with t and a k. Right? Here, this becomes so let me do this here. So rho is k over t, and so this is k square. Right? Rho cancel, so that's k square d by dt, t d by dt. Right? There's a factor of k square remaining plus k square times j0 of t is equal to 0. K square can leave the place because that's just multiplying it all through. So often in a single variable, this will be t plus 1 times j0. Various ways of looking at it. And again, this is equal to second derivative of t squared plus 1 over t by t plus 1 j0 t. Often in practical problems, you want to see the k in it, but whenever you have a mathematical description, this is easier to work with one variable, a dimensionless variable. Okay, so that's good. Let's now introduce the nth order Bessel function. And for that, let's look at this exponential. Any questions at this stage? Does this remind you of anything? You guys might have done it somewhere of this thing, little bit of something. Probably yes, no, probably not. Yes, maybe. So if not, it's useful. Yeah. Okay. So let's. So again, we are introducing a new feature, new function here. So this is called. Let's call this. So this is a generating function. Or Bessel function. Like remember legendary polynomials also we saw a generating function. The idea is that you have one function, expand it as a series and the coefficients are identified as the particular function. So here also the generating function here is, as we saw for the zeroth order, this is going to be e raised to I t cosine alpha. That's our basic function here, but now we want to put something in here. Let's write this as cosine alpha is e raised to I t I alpha plus e raised to minus I alpha over 2. There's an exponential in the power of the exponential, but that's correct. It's okay. Now let me substitute. Let me write this as exponential of just rewriting this. As this is I times e raised to I alpha. I brought the I in. And the second I want to write this as I times e raised to I alpha. So I put this in the denominator, and I put it in the denominator, so that's as a minus sign. That's just a way to motivate the structure. So that seems to suggest that I can call this temporarily as e raised to I alpha. Let me introduce a new variable u. That's just temporary, but if you don't want to introduce it, just explicitly write that. It's equal to e raised to t by 2 times u minus 1 over u. With u being this. We cannot argue that that's just an observation, right? Nothing new in this. But now we want to expand this as a series. There are two variables here, right? T and u. I can expand this in one of the variables. Let's expand in terms of u. That's going to be u raised to m. But most of the functions can be expanded like this, so minus infinity to plus infinity. But when I expand something, there are coefficients in front. Right? When I expand some function in terms of a power series, there are coefficients, and those coefficients is what we will define as the Bessel function. But that will be dependent on t. That will be dependent on t. Right, so these are coefficients in the series expansion. That's one simple way of looking at it, but we define this to be Bessel function of mth order now. Okay, so that's just a definition, but then the question goes, what is it? What exactly is of m? And let's look at that. Let's go back to this one, right? So e raised to p by 2 u times 1 over u. I want to expand this in terms of u. I know expansion of exponentials. So that's t by 2u times exponential of minus t by 2 1 over u. That's straightforward, but I know how to expand an exponential. That's n equal to 0 to infinity. 1 over n factorial times t by 2 times u raised to n. Right? That's one of the series. Second one also can be expanded similarly. You see k equal to 0 to infinity and 1 over k factorial and minus t by 2 1 over u raised to k. That's perfectly fine. And the goal now is to get the powers of u and compare it with that. But power of u, so let's see what this is equal to. There are double sums now here. K equal to 0 to infinity. Let me collect all these things. There's a minus 1 raised to k. There's an n factorial. There's a k factorial. There's a t by 2 raised to n plus k. And there is a u, which is n minus k. So I do see the coefficient here. It seems to be the Bessel function, but this is not in um, right? So it's not, it's an n minus k. It's a combination of two variables. So we are let's do a resummation here. So this is a general idea again, always shows up in summations like this or in identifying functions. So notice what is the kind of sum that's going on here. So we have a summation in k and summation in n. And we are going for k greater than 0, right? So that is k equal to 0, 1, 2, 3, 4, 5, and so on. And n is equal to 0, 1, 2, and so on. So there's a discrete sum. So that's this. The first quadrant everywhere you have to sum. For each point here, there is a contribution for this. But I would like to get this in terms of a single variable n minus k. So I would like to substitute m is equal to n minus k. That's what I would like to substitute. But where is that in here? So look at it as an equation. So n is equal to k plus m. So n is equal to k plus 1 is a straight line with a slope of 1 and an intercept of m. So that seems to suggest that these are straight lines. So that's an equation of n is equal to k plus m, like all these lines for various m's. Is that clear? Those are lines with n equal to k plus m. But then extend this backward a little. And if I were to look at it in this direction, that's my y-intercept, which is m. That's my m. With this being m equal to 0, this being m equal to minus 1, that being m equal to minus 2, and so on. Right? So it's just a resummation property here. So instead of going, so if I want to sum these quantities, the order of summation doesn't matter, right? When you're adding 3 plus 2 plus 5, whether I add 3 plus 2 first or 2 plus 5 first, it doesn't matter, it's associative. So I can change the order of integration, order of summation, and substitute sum over m and k. But where is the value of region of integration or summation from m? M goes from plus infinity to minus infinity. Right? Because if I want to get this point, it is minus 3. If I want to get this point, that's plus 3. As I get further and further, m has to scan from minus infinity to plus infinity. Is that clear? Roughly? Right? Think about it, because it's relatively straightforward, just here to argue things out. And k still can go from infinity to 0. So the substitution we are making is m is equal to n minus k, and k stays k itself. That's the two substitution you make, and you want to change your summation accordingly. So you're going from not n and k, you're actually now going from m equal to minus infinity to plus infinity, and k going from 0 to infinity. And now you want to change everything in terms of m and k. K remains minus 1 is to k. N is equal to k plus m. And p by 2 times n is k plus m, so it's m plus 2k. And u is just m. And that's all you need to do, because now you have identified your jm. Whatever sits here, that's your jm. As a series, we didn't get it as an integral, but we'll do that in a minute. That's straightforward. So we learned that jm, the Bessel functions of nth order, is actually equal to k equal to 0 infinity minus 1 is to k over m factorial times m plus k factorial and p by 2 m plus 2k. It's good to see what is J0 of t. It has a series. If it is J0, m is 0. So when k is equal to 0, that's 1, k factorial, k is 0, m is 0. So it is just starts as 1. K 0 starts as 1. Next one is minus k equal to 1. So this is t over 2. That's t over 2 squared. M is 0, k is 1. So that's t over 2 squared. And let me do one more term. So that's plus t over 2 cube. Sorry, 4, right? 4. And now k is equal to 2. So 2 factorial, 0 factorial. That's 1 over 2. So let's see. J 0 has a series expansion. You can get this for various J0s, but we were interested in the integral representation. Let me take one more minute and we will actually motivate it again next time. We'll begin with that next time. But let's just very quickly go back here and we have e raised to it cosine alpha is equal to u of m j of mt, right? So this is m equal to minus infinity to plus infinity. U was I, so it is I raised to m times e raised to I m alpha, and then this j of t. This is a series, and if you think of this as a series in this, what is this? What kind of series is this? When you expand something as a function of exponential with m going from minus infinity to plus infinity, what kind of series is this?
Like a Fourier series?
Fourier series, right? Because it's a sine and cosine. That's a Fourier series. So I can invert this, right? We'll do that again next time more carefully. But if you just Fourier invert this, that gives me my j of mt. And let me write that I m there itself. So Fourier is d alpha, right? So again alpha. So that is d alpha over 2 pi. So you can say that Bessel functions of nth order are the Fourier transformation of exponential of it cosine alpha. So that's another way of thinking of this. But then now this is e raised to minus I m alpha and it cosine alpha. Okay. I will motivate this more. We'll start from here next time. Let me stop. And we will do orthogonality, which is an important relation, and some what is called addition formula for Bessel functions. Okay. That's all. Thank you. I can put the camera on 1%. One with Moses.
Thank you.
Yeah. Thank you. Enjoy. Okay.